Hello, everyone, and welcome to today's presentation. I'm excited to have you here as we explore the mechanics and physiology of lung ventilation. The title of our session is Mechanics and Physiology of Lung Ventilation, with a focus on understanding pressure-volume relationships, lung compliance, and the important role of pulmonary surfactant. Over the next few slides, we'll delve into how the lungs work during breathing, what influences their flexibility, and how surfactant helps us breathe more easily. Let's get started. Now, let's explore how mechanics and physiology work together to enable lung ventilation. First, we have Hooke's law, which is fundamental in understanding lung expansion. Basically, it states that an elastic structure, like lung tissue, changes its size proportionally to the force applied. So when we breathe in, the lungs stretch because of this elastic property. This law helps us understand how lung tissues stretch during inflation. Next, we look at pressure-volume relationships. These are critical because they describe how the lungs and thorax work together during ventilation. The way pressure and volume interact determines how air moves in and out of the lungs. Essentially, the elastic properties of the lung-thorax system govern this process, making it essential for effective breathing. Finally, let's focus on the role of pressure in lung inflation. Increasing pressure inside the lungs causes them to stretch, which inflates them. This process is at the heart of ventilation mechanics. Without this pressure-driven expansion, efficient breathing wouldn't happen. So, understanding how pressure influences lung expansion helps us grasp the core principles of respiratory physiology. Let's take a closer look at the mechanics and physiology of lung ventilation, specifically focusing on static pressure-volume relationships and elastic limits. When we talk about lung inflation under static conditions, we're really examining how the elastic properties of the lung-thorax system come into play. This relationship is key because it helps us understand how changes in pressure directly affect lung volume. Now, as pressure increases, you'll notice that lung volume tends to increase proportionally. That means if you gently raise the pressure, the lung expands in a predictable, linear fashion, up to a certain point. This proportional increase is important because it shows us that the lung can safely expand within a certain pressure range without any damage. However, there is a limit, the elastic limit. Once we pass this threshold, additional pressure causes little to no further increase in volume. Think of it as the lung reaching its maximum stretch capacity. This is a critical point because it signals the boundary of safe lung expansion. Exceeding this elastic limit is risky. Pushing beyond it can lead to lung rupture due to overextension, which is something we definitely want to avoid. So, understanding these elastic properties and limits is essential not only for grasping normal lung function, but also for recognizing the importance of staying within safe pressure ranges to prevent injury. Let's explore the mechanics and physiology of lung ventilation by looking at how inspiration and expiration follow different paths. During breathing, the lung volume at a given pressure actually varies depending on whether we're inhaling or exhaling. This means that the process isn't simply the same in reverse, it has its own unique pathway. Now, a key point here is the nonlinear nature of the lung's pressure-volume curve. If you imagine plotting pressure against volume during inspiration and expiration, you'll notice the curve isn't a straight line. Instead, it has a complex, curved shape. This nonlinearity reflects the intricate behavior of lung tissues and airway dynamics, meaning the lungs don't expand and recoil in a perfectly linear fashion. This complex curve actually tells us a lot about how the lung tissue responds during each breathing cycle. It shows that the tissue and airway mechanics are quite sophisticated, influencing how easily the lungs can expand or contract at different pressures. Airway dynamics, in particular, play a significant role in shaping this nonlinearity, affecting our breathing efficiency and comfort. Overall, understanding these paths and the nonlinear pressure-volume relationship helps us grasp the detailed mechanics behind ventilation, emphasizing how complex and finely tuned our respiratory system truly is. Let's talk about hysteresis in lung compliance. As you may know, this refers to the energy differences involved in inflating and deflating the lungs. Interestingly, more energy is needed to inflate the lungs than to deflate them. The reason for this is that during expiration, the alveoli are already open, so less force is required to let the air out. Now, if we look at the deflation versus inflation limb of the lung compliance curve, hysteresis describes how these two parts are different. Specifically, for the same amount of pressure applied, the lung volume during deflation is actually higher than during inflation. This ties into how lung volume behaves at any given transpulmonary pressure. During deflation, the volume remains higher because of the mechanics involved in alveolar opening and closing. Essentially, alveoli tend to stay open longer during deflation, which affects the energy needed and the lung volume achieved. Understanding hysteresis really helps us grasp the differences in lung mechanics when we breathe in versus breathe out. It also sheds light on the energy dynamics at play during respiration, which is crucial for understanding lung function and efficiency. Let's talk about alveolar recruitment during lung inflation. At the very start of inspiration, some alveoli are actually closed, with their walls stuck together. To open these closed alveoli and allow air in, the body increases the transpulmonary pressure. This pressure essentially forces the alveoli open, making room for air to enter. Now, the role of transpulmonary pressure here is crucial. As it increases, it helps recruit those alveoli that were previously closed by pushing their walls apart. Interestingly, alveoli that are already open don't change much in size during this process. They stay relatively stable. This recruitment process is really important because it allows the lungs to expand efficiently during inspiration. Without opening those closed alveoli, lung volume wouldn't increase as effectively, which makes alveolar recruitment a key part of healthy breathing. So, in essence, the ability to open those alveoli ensures we maximize lung capacity each time we breathe in. Let's take a closer look at the mechanics and physiology of lung ventilation, starting with the concept of lung compliance. Lung compliance, or CL, is essentially a measure of how easily the lungs can expand or distend when they are being inflated. Think of it as the lungs' opposition to inflation, how much effort it takes to stretch them. It's defined as the change in lung volume that occurs with a 1-unit change in pressure, typically measured in liters per centimeter of water pressure, or L/cm H2O. Now, when we talk about high compliance, we're referring to lungs that inflate quite easily. This means there's minimal resistance to stretching, and the lungs don't require much pressure to expand. High compliance is generally a sign of healthy, flexible lungs. On the other hand, low compliance indicates that the lungs are stiff and resistant to inflation. In this case, it takes more pressure to achieve the same amount of expansion, which reflects increased resistance. This can happen in conditions like fibrosis or acute respiratory distress syndrome, where lung tissue becomes less elastic. Understanding these differences helps us evaluate lung function and tailor ventilation strategies effectively. Remember, compliance is a key factor in assessing how well the lungs respond to mechanical ventilation and overall respiratory health. Now, let's take a closer look at the mechanics and physiology behind lung ventilation, specifically focusing on lung compliance and volume. As the lung volume increases, lung compliance actually decreases. This happens because when the lung fibers are stretched, they generate a greater elastic recoil. Think of it as the lungs becoming more resistant to further expansion once they've stretched out quite a bit. This relationship really underscores the biomechanical limits of how much our lungs can expand safely and effectively. Next, during exercise, this recoil force plays a vital role. When we breathe heavily, our lungs reach larger volumes, which increases the recoil force. This helps us produce higher expiratory flow rates, meaning we can expel air more forcefully and efficiently. It's a key mechanism that helps meet the increased oxygen demands during physical activity. Finally, it's important to understand that lung compliance isn't a static property. It dynamically adjusts based on lung volume, supporting efficient ventilation across different physiological states. Whether we're at rest or exercising, This flexibility allows our lungs to adapt and maintain optimal function. This dynamic adjustment is fundamental to our overall respiratory efficiency, aligning perfectly with the broader theme of how our respiratory system is finely tuned to meet varying demands. Let's discuss the implications of lung compliance, which is a key factor in understanding how well our lungs can expand during breathing. When we say high compliance, it means the lungs can inflate easily with little effort. Think of it as being very stretchy or flexible. On the other hand, low compliance indicates that the lungs are more stiff and require more effort to expand, making breathing more difficult. Now, focusing on static lung compliance measured at the functional residual capacity, or FRC, the normal value is about 0.2 liters per centimeter of water pressure, or 200 milliliters per centimeter. H2O, this measurement gives us an idea of how easily the lungs can expand during a normal breath. Understanding normal lung compliance values is essential because they serve as a baseline. When lung compliance deviates from this norm, it often points to underlying issues. For example, diseases can alter lung compliance significantly, either increasing it or decreasing it. Such changes are not just numbers, they have real impacts on respiratory function. For instance, reduced compliance can make breathing labored and inefficient, which is often seen in conditions like fibrosis. Conversely, increased compliance might be seen in cases like emphysema, where the lungs become overly stretchy. Overall, recognizing how disease states influence lung compliance helps us better understand respiratory challenges and guides us in tailoring appropriate treatments. Let's take a closer look at high lung compliance in emphysema. When someone has emphysema, it causes the loss of elastic lung tissue, which means the lungs can stretch more easily, but they don't recoil as well. This structural change really shifts the mechanical properties of the lungs, making them more distensible. Now, because of this increased compliance, small changes in pressure can lead to large increases in lung volume. This is a key feature of emphysema, abnormally high compliance. It means the lungs are overly stretchable, but that comes with some problems. For example, because the lungs don't recoil effectively, emptying the lungs becomes difficult. This impaired ability to exhale fully affects overall respiratory efficiency. So, while the lungs can stretch easily, their ability to return to normal size is compromised, leading to breathing difficulties. Overall, this abnormal compliance is central to understanding the mechanics of emphysema and how it impacts breathing. Let's take a closer look at lung compliance in pulmonary fibrosis. When the lungs are affected by this condition, higher pressures are needed to inflate them. This means that the lungs are less compliant, or in other words, they don't expand as easily as healthy lungs do. Now, what causes this? Pulmonary fibrosis is characterized by an increased lung recoil force, which makes the lungs feel stiff, what we call stiff lungs. This stiffness hampers their ability to expand properly and ultimately reduces the total lung volumes. So, in essence, because the lungs are less compliant and more recoil-prone, they can't take in as much air as they normally would. This significant reduction in lung volume is a direct result of the stiffness caused by fibrosis, which is a crucial point to understand in considering how pulmonary fibrosis affects respiratory function overall. Let's talk about the impact on alveolar stability. Without the counteracting forces in the lungs, surface tension would cause the alveoli to collapse, leading to atelectasis, which is essentially the collapse of part or all of a lung. This highlights just how critical the balance of forces is for maintaining proper lung function. Now, where does surface tension come from? It arises because water molecules at the alveolar surface are attracted to each other, creating a contracting force. This force tends to shrink the alveoli and plays a major role in lung recoil pressure, which is the force that helps the lungs return to their resting volume after inhalation. Understanding surface tension in the lung is key to grasping lung mechanics overall. It significantly influences how the lungs behave during breathing. Specifically, it affects the lungs' recoil pressure, which in turn impacts respiratory efficiency. So, maintaining the right balance of these forces is vital for effective ventilation and overall lung health. Now, let's talk about the function of pulmonary surfactant. Pulmonary surfactant is a crucial substance found in the alveolar fluid, and its primary role is to reduce surface tension. By doing so, it decreases the effort required to breathe and lowers the pressures needed to keep the alveoli open. This is essential because, without surfactant, the alveoli would tend to collapse, especially during exhalation. Next, let's look at where this surfactant comes from. It is secreted by specialized cells known as type II alveolar cells. These cells are vital because they help maintain alveolar stability, ensuring that the lung structure remains functional and efficient for gas exchange. Finally, the role of pulmonary surfactant in alveolar stability is particularly important. It stabilizes the alveoli by preventing their collapse, which is fundamental for efficient gas exchange. Without surfactant, alveoli would be at risk of collapsing, especially during exhalation, compromising the entire process of oxygen entering the blood and carbon dioxide leaving it. So, in essence, surfactant is a key player in maintaining healthy, functional lungs. Now, let's explore how surface tension impacts alveoli. Without surfactant, smaller alveoli require higher distending pressures than larger ones because of the constant surface tension. This highlights just how crucial surfactant is in maintaining alveolar stability and preventing collapse. Next, understanding Laplace's law helps clarify this relationship. The law is expressed as P equals 2T divided by R, where P is the pressure inside the alveolus, T is the surface tension, and R is the radius of the alveolus. This formula shows us how pressure, surface tension, and alveolar size are interconnected in the lungs. Finally, what happens if surfactant is absent? Smaller alveoli tend to empty their air into larger ones, which can destabilize the lung structure. This process underscores the vital role of surfactant in preventing alveolar collapse and ensuring smooth, effective lung function. Now, let's talk about surfactant and surface tension in the lungs. Surfactant plays a crucial role because it adjusts surface tension based on the size of the alveoli. It does this by lowering the surface tension more in smaller alveoli, which is really important for maintaining uniformity. This adjustment helps to equalize the recoil pressures across alveoli of different sizes. Without this, smaller alveoli might tend to collapse into larger ones due to higher recoil pressures. So, surfactant ensures that all alveoli inflate evenly and stay stable. This concept ties directly into Laplace's law, which explains how surface tension affects alveolar stability. By decreasing surface tension in smaller alveoli, surfactant prevents collapse and promotes uniform inflation pressure throughout the lungs. Overall, surfactant is vital for alveolar stability, ensuring that even the smallest alveoli stay open and functional during breathing. Let's talk about the effort involved in alveolar recruitment. This concept is all about the initial work your lungs do to open up alveoli that have collapsed. During inspiration, your lungs need to overcome a certain pressure to open these alveoli up so that gas exchange can occur efficiently. This is where the critical opening pressure comes into play. The critical opening pressure is essentially the high pressure required to open a collapsed alveolus. Once that pressure is exceeded and the alveolus opens, it then expands easily with less additional effort. This is a key point because it highlights how much effort is needed at the start of inspiration to get the alveoli functioning properly. Understanding this concept is especially important in managing respiratory conditions. If we know the critical opening pressure, we can better tailor ventilation strategies to ensure alveoli open without causing damage. It also gives us a clearer picture of the mechanics behind alveolar expansion and the effort needed for effective breathing. So, in summary, the effort to open collapsed alveoli hinges on overcoming this critical opening pressure, which is vital for efficient ventilation and overall respiratory health. Now, let's take a closer look at the composition and secretion of pulmonary surfactant. The key point here is that type II alveolar cells are responsible for secreting surfactant through a process called exocytosis. Essentially, these cells release lamellar bodies into the alveolar liquid lining, which is crucial for maintaining proper lung function. When we talk about what surfactant is made of, it's about 90% polar phospholipids and 10% protein. This unique mix is vital because it allows surfactant to reduce the surface tension within the alveoli effectively. This reduction in surface tension plays a fundamental role in lung mechanics. It helps maintain the levels of surfactant needed for optimal lung expansion. Without it, the alveoli could collapse, especially during exhalation, making breathing much more difficult. So, in essence, the secretion and composition of pulmonary surfactant are both critical for ensuring that our lungs can expand properly and function efficiently throughout the breathing cycle. Today, I want to talk about the crucial role of surfactant in neonatal breathing. Essentially, for a newborn to breathe successfully right after birth, there must be enough surfactant present in the fetal lungs. This substance is vital because it reduces surface tension within the alveoli, preventing them from collapsing. Without sufficient surfactant, the alveoli tend to collapse easily, especially at low lung volumes, which makes gas exchange much more difficult. This brings us to a particularly important point for premature infants. Often, these bobbies haven't produced enough surfactant yet, leading to a condition called respiratory distress syndrome, or RDS. The lack of surfactant means their alveoli can't stay open, which hampers their ability to oxygenate blood effectively. Understanding this connection highlights how critical surfactant is for neonatal respiratory health. When surfactant levels are adequate, alveolar stability is maintained, ensuring efficient gas exchange and healthier breathing. Conversely, surfactant deficiency in premature infants underscores why they are more vulnerable to respiratory issues right after birth. In summary, surfactant is a key player in maintaining alveolar stability and supporting neonatal respiration, especially in those born prematurely. This underscores the importance of surfactant in the broader context of lung mechanics and respiratory physiology. Now, let's discuss how surfactant plays a crucial role in reducing the effort needed to breathe. Essentially, surfactant decreases the surface tension within the alveoli, which makes it easier for the lungs to expand and contract during each breath. By lowering the distending pressures required to keep small alveoli open, surfactant helps prevent alveolar collapse and reduces the overall work of breathing. Moving on to alveolar stability, surfactant is key in stabilizing alveoli of different sizes. This stabilization ensures that gas exchange remains efficient across all alveoli, regardless of their size. When alveoli are stable, oxygen can be absorbed effectively, and carbon dioxide can be expelled without unnecessary effort or complications. Finally, let's consider the physiological benefits of pulmonary surfactant beyond just reducing effort. It also helps prevent fluid from leaking out of the pulmonary capillaries into the lung tissue. This is vital because it keeps the alveoli dry, which in turn maintains optimal respiratory function. When the alveoli stay dry and stable, the lungs operate more efficiently, supporting overall respiratory health.